I'm happy to have introduce Subhabrata Sen of Harvard for the first talk of the morning, and he'll tell us about principal submatrix recovery.
Thanks so much, Ryan. Let me just share my screen. Okay, does that look good? Okay, so thanks so much to the organizers for the wonderful workshop. Thanks so much for the invitation to speak. We've had some really wonderful talks so far. So today I want to talk about the overlap gap property for submatrix recovery. This is based on joint work with David Gomarnik and Ankush Jagannath. So the premise for this talk is sort of in these statistical versus computational trade-offs. We've heard a lot about this so far in this workshop. There has been accumulating evidence that there are sort of quite a few high-dimensional statistics problems where sort of optimal statistical inference might be impossible to do using computationally feasible methods in certain regimes of the parameter space. And evidence for this has been provided using very, very different techniques, such as average case reductions, analysis of AMP type algorithms, sum of squared lower bounds, and so on and so forth. We've heard about quite a few of these approaches so far. In contrast to that, I want to talk about some structural evidence for hardness in the average case. So I'll talk about a very specific problem, which is related to planted submatrix recovery. And we'll see what this structural evidence actually gives us formally in terms of hardness for specific algorithms. But in general, I think this approach is intuitive and sort of useful because it kind of suggests why it might be difficult to solve this problem, at least with certain classes of algorithms. Okay, so I'll talk about principal submatrix recovery. So the setting is that we get to see an n by n symmetric matrix. Most of the entries of this matrix are Gaussian with mean 0. However, there is a hidden planted submatrix where the mean has been elevated to be lambda over n. And I'll talk about a setting where the size of this planted submatrix is n rho by n rho. And the background Gaussians have been scaled so that the spectral norms of the planted matrix and the background noise are on the same scale. And of course, this problem sort of exhibits slightly different behavior depending on the size of the planted submatrix. So today I'll look at a very specific regime where the size of the planted submatrix is actually linear in the size of the ambient matrix, but the leading constant is very tiny. So I'll sort of formally look at a double asymptotic regime where first the size n tends to infinity and then rho goes to 0. Okay, so this sort of I think is useful to think of in terms of problems such as sparse PCA. I think we'll hear from Elias a bit more about this setting in the next talk. So given this general setting, there are certain questions that are of natural interest. So the first and basic question is, if I give you this matrix, can you detect the presence of this planted submatrix? So can you tell me whether this is just plain noise or whether there is some signal or not? And then if you can actually distinguish this matrix from pure noise, the question naturally becomes, okay, can you actually recover this submatrix? And naturally here we will also ask the question, can we actually recover it efficiently? So one point that I actually want to emphasize here is that the corresponding detection question in this particular setting is actually trivial. This is because if you just sum the entries of the matrix, in this regime, it is very easy to see that the sum-based statistic will distinguish between the null that lambda is 0 versus the alternative that lambda is positive for any lambda. Okay. And I just wanted to make this point because we've heard quite a few talks so far in this workshop where even the detection question is hard. So this is sort of a slightly different problem in that detection is actually fairly easy, but estimation is somehow hard. Okay. So today we'll basically focus on the second two questions, right? How well can we recover this planted submatrix, and can this be recovered efficiently? Now, let me spend a few moments describing the history of this problem. So a Bayesian version of this problem where my matrix can be represented as a one-rank spike of a GOE matrix. So one natural Bayesian formulation is where the entries of the spike are IID from a certain distribution. So back in 2014, Deshpande and Montanari, they initiated a study of this setting where the entries of the spike were IID Bernoulli with probability rho. They analyzed the behavior of the Bayes optimal AMP, and they concluded that there is some critical density rho, such that if rho is bigger than this rho critical, then AMP-based algorithms will perform Bayes optimal inference in this problem. This was followed up on in subsequent works by Lesieur et al. They actually started exploring this double asymptotic where first n goes to infinity and then rho goes to 0. And they, based on the analysis of the state evolution system that arises from AMP-based algorithms, they concluded that there should be a hard phase in this problem, in this scaling. I should also remark that on the theoretical statistics end, there has been a lot of exploration about submatrix recovery per se, and people have figured out the information theoretic limits as well as sort of computational barriers and stuff. But one crucial difference from what we will be looking at today is that on the statistics side, the question has usually been about exact recovery. So this is usually referred to as the submatrix localization problem. And that has sort of a substantial literature on its own right. But these two, I mean, our results are not directly comparable with theirs because our metrics will be slightly different. Okay, so what will we be doing today? So we want to look at this problem, and I want to provide you some rigorous evidence based on the characteristics of the problem that inference might be hard in certain settings. Now, to do that, I will be looking at the behavior of the maximum likelihood estimator in this setting. And I'm happy to talk about whether the MLE is the best thing to do in this setting or not, but I think even this will provide us with some good intuition. So the maximum likelihood in this problem basically reduces to this discrete optimization problem where we seek to maximize this quadratic form in the matrix M. M is the matrix that we have observed, subject to these constraints. So the vector X is a binary vector and it has exactly n row many elements that are 1. This encodes the fact that I'm looking for n row by n row submatrices. And our metric for our estimators is what we'll refer to as approximate recovery. So the point is, can we recover a linear proportion of the hidden support, right? So you should think of the constant C here as some universal constant like 0.1 or 0.5. So you want to recover some fixed proportion, and the C is independent of both n and rho. Okay. So our first result is of an information theoretic nature, and it identifies the signal strength that you need for approximate recovery, right? So it first says that, So it first says that if lambda is actually little o of square root 1 over rho log 1 over rho, then approximate recovery is impossible. On the other hand, if lambda is bigger than 2 square root 1 on rho log 1 on rho, then the maximum likelihood estimate actually performs approximate recovery, right? So this identifies the information theoretic threshold that one needs for this purpose. However, if you go back and look at our maximum likelihood problem, you see that, okay, this is a discrete optimization problem. As such, we don't quite know of a natural way to do this efficiently. So you might say, okay, what are simple algorithms that I can use? And a simple algorithm would be a naive spectral algorithm that would basically look at the top eigenvector of this matrix and round its entries suitably to construct a binary vector with exactly n row many ones. Okay. And this is definitely very easy to see just using properties of Gaussian random matrices, that you need lambda to be bigger than 1 over rho for the naive spectral algorithm to work. Okay, so note that 1 over rho, when rho is small, is actually much bigger than the square root 1 over rho threshold that you need for MLE to work. And so this brings us to sort of this natural question: what happens for intermediate signal strengths lambda? Right. So to explore sort of what happens there, I'd like to look at sort of a restricted version of the likelihood. Okay, so what this does is that it maximizes the likelihood subject to an additional constraint that I actually have a fixed n times q overlap with the underlying truth. So in terms of matrices, you should think that, okay, I have my planted submatrix, and I'm specifying that I will maximize my likelihood subject to a certain number of rows and columns that I will have in common with the planted truth. Okay. Now, one point, of course, to note is that this is, of course, a theoretical construct. We will study this to understand properties of the problem, and this is not something that we can compute given the data, right? Okay, so one of our main technical results is to conclude that this restricted likelihood function for every value of q actually converges to a deterministic limit. This deterministic limit is phrased in terms of Parisi type formulae. We'll come back to this in a bit. So this is some fairly involved formula, but it's explicit at least, right? And we know that this is sort of a deterministic formula in the limit where n tends to infinity. Now, let's try to see what sort of intuition we can gain by actually looking at the properties of this function e. To develop some intuition, let's say I actually plot this function e as a function of q for different values of lambda, right? Okay, so what will happen? Let's think of a simple case first. So if lambda is 0, this is the case where I have no signal, and therefore it's all impossible to detect the planted matrix. And so I will expect my function e to basically be unimodal and have its maximum at rho squared, right? This is the sort of random overlap point, and then we'll have sort of a maximum there. On the other hand, if lambda is very, very large, what will happen is that this function will still be unimodal, but the maximum will shift, and the maximum will actually be attained at some constant times rho. Okay, this is the regime where the MLE actually will perform approximate recovery. And sort of, at least in this regime, it is suggestive that, if I start any local algorithm and if I initialize it at random, I will start at somewhere near rho squared. And so it is suggestive that maybe we'll be able to climb this hill and get to the top. The main sort of takeaway is that we can formally prove that there is sort of this intermediate signal regime where lambda is sort of 1 over rho to the half plus alpha for some alpha sufficiently small, where this restricted likelihood function has this non-monotonic property. Okay, and the reason why we call this a version of overlap gap is that if you look at sort of configurations of submatrices that have likelihood values beyond a certain level, then its overlap with the planted truth could either be very large or be very small. And actually, we have sort of a gap in the middle. This is the sort of set of overlaps that cannot be attained. So in this sense, this is sort of a version of overlap gap. And one point to emphasize here is that in contrast to sort of unplanted problems, here we look at an overlap with the planted truth rather than overlaps between two IID samples. Okay, so, right. As a formal consequence of our results, what we can prove is that a simple family of local Markov chains will not be able to perform approximate recovery in this regime of signal to noise ratio. So one natural thing to do is that if you want to maximize the quadratic form, you run a Markov chain which has stationary distribution, a Gibbs type distribution corresponding to beta, where beta is very large. And the formal result here, let me not parse the entire thing in step, but the takeaway message is that if you are initialized sort of near rho squared, so at random, and if you run this local dynamics, then it takes you exponential time to sort of escape the local maximum near rho squared and sort of get to the global one. Okay. So let me pause for a second here to see if there are questions regarding sort of our main results and sort of the main takeaways. Okay. Okay, so in sort of the time that I have left, maybe I can talk a bit about the sort of some proof ideas and highlight sort of how we went about doing this. So as I said, the main technical sort of ingredient was a Parisi type formula for this restricted likelihood function. And then sort of one had to actually analyze the behavior of this variational formula in the scaling limit where rho goes to 0, right? Our proofs for the information theoretic result, I think, are sort of more standard, and they use relatively straightforward information theoretic techniques. Initially, we only had this result, the negative result for the MLE, but one of our referees pointed out a very clever improvement so that we can now rule out other estimators as well. But let me actually talk about the overlap gap analysis in this context. So the relevant Parisi formula that arises is the following. Sorry, there's a lot of text here, so let me go over this slowly. So the first simplification, of course, is that without loss of generality, we can assume that the planted matrix is sort of at the top and left corner, right? This doesn't change the problem at all. In this case, we will end up with a variational problem on an infinite space corresponding to paths that are non-decreasing. These also came up in Ahmed's talk a few days ago. So the variational parameter here, at least one of the variational parameters here, will be a function m, which is non-decreasing. And then we'll sort of, it's easier to phrase it in terms of a measure mu, which has density that is m. And lambda1 and lambda2 sort of are two real numbers. These are two Lagrange parameters that actually enforce the constraints that there are exactly n rho many ones and sort of nq many ones that are overlapping with the planted truth. Okay, and so the eventual Parisi formula here sort of is, so you have sort of two Parisi type terms that come up. These are solutions of these nonlinear PDEs started from this final time configuration. And as I mentioned before, lambda1 and lambda2 are my Lagrange parameters, right? The final form for the restricted ground state energy in physics terms and the restricted likelihood in a more statistical terminology is sort of a lambda q squared. This is sort of the overlap contribution that you have to your energy from the planted truth, and then sort of the noise contribution. Okay. Now, to analyze sort of the overlap gap, formally, what we do is that we directly analyze this restricted energy. So we take a derivative in Q, you get sort of a linear term which increases, and then the main complicated term to analyze arises in terms of the difference between these two Lagrange multipliers. So technically, the main challenge is to analyze their behavior for different values of Q in the limit when rho goes to 0. Okay, and formally, this is sort of what we actually establish to show overlap gap, right? So we show that at rho squared, this derivative is positive. there is some point which is little o of rho where this derivative is negative. So we know there is some point which dominates both of these in the middle. And then in the signal to noise ratio regime where lambda is like 1 over rho to the half plus alpha, the maximum is actually attained beyond the point Q2, right? So that suffices for us. And I'd just like to add that the main difficulty that arises from analyzing this lambda 2 and lambda 1, what we can do here is that our main idea is to utilize sort of recent advances in the study of mean field spin glasses and Parisi type variational problem. And there, a natural diffusion that comes up is related this is a diffusion that has a Brownian component and a drift, which is given by the first derivative of the function in itself. This also came up in Ahmed's talk, and these Lagrange multipliers are characterized as fixed point equations in terms of this SDE. So for example, just to give you a flavor of this analysis, if your first term were absent, so for example, if these diffusions were just Brownian motions, then you could exactly identify these lambda I stars in terms of the quantiles of a Gaussian distribution, and you could directly analyze their behavior for different values of Q. The main difficulty that arises is that we don't really know how the drift term behaves, and we have to be a bit hacky about it. And that sort of gives us whatever we can prove. So let me emphasize one point here is that, our results related to overlap gap that I emphasized, we can prove this only for alpha sufficiently small. I think evidence that arises from low degree likelihood based methods that Elias will present, I think, right after this, they suggest that actually the threshold, the computational threshold should be at 1 over rho, where our spectral algorithm works. So I think it would be really interesting if we could prove the existence of overlap gap up to 1 over rho. At this point, we can prove it maybe up to 1 over rho to the 0.6. And the main barrier that we have been facing so far is that we don't really have a very good way to exactly analyze these lambda I stars. So if one could do this analysis a bit more accurately, this would probably improve the bounds. And I actually believe that it should be able to prove that the OGP persists up to 1 over rho, but so far we don't really have that. So following our results, there has been actually quite some progress on this problem. So the actual mutual information in the related Bayesian version of the problem, when rho is actually converging to 0 with n, that has been worked out in a set of papers by Jean Barbier and his collaborators using the adaptive interpolation method. So Gerard, Alex, and Elias have actually extended some of this analysis to the case where rho actually converges to 0. I think Elias will talk at length about this in the next talk. And there has been a very recent paper by Salil and Alex where they actually establish estimation lower bounds in this context using the low degree likelihood methods and stuff. So I think that's also very interesting. And yeah, I think sort of these results have added additional perspectives to this problem. So let me finish here. Thanks so much for your attention. Let me know if there are questions.
Thank you, Subhabrata.
Thank you.
Great. So time to quiz Subhabrata, who has some questions for him on that talk.
Maybe go ahead.
I have a question related to the definition of those Lagrange multipliers, the stationary conditions. Yeah, in this slide. So the last line, I can't parse the last line. So is that an expectation, or like there's something missing in that probability?
Sorry. Yeah, that's a typo. Thanks, Ahmed. I wanted to say that I want these probabilities that I think these are bigger than equal to 0.
Bigger,
given that
okay.
the are started at 0.
And
Yeah.
does that define the, does that tell you the law of these lambda stars? Or I mean, I guess the value of those lambda stars?
Yeah, because all I want, so if you think about it, if you knew this exact solution, right, then these are diffusions. So you want a corresponding quantile of that diffusion, right? So it's a random variable. You want it identifies the lambda i's in terms of the law.
I see.
Pointing out the type.
Got it. Yeah. Thanks. Yeah.
I believe Sam has a question for you.
Hey, Subhabrata.
Hey.
Can you say a little more about what kind of algorithms this rules out? So you said something about local Markov chains, but like sometimes these kinds of results, my understanding is that they really only can understand what happens when you initialize in some kind of very funny way, like the Markov, the Gibbs measure conditioned on low overlap instead of random initialization. And
that's there. Yeah, I kind of skipped over that, but that's a very fair point. So what this can formally rule out is local Markov chains that are started from the Gibbs distribution, initialized at rho squared overlap. I think the point is that, okay, from a physics perspective, I guess it would be natural to believe that that would look like an IID initialization, but
sure,
that's not really formal. And in general, I think one question that I think is very important to answer is sort of whether these structural results actually imply barriers for other classes of algorithms as well. I think if one could prove this in more generality, then it would be definitely something more, more important and interesting.
What is the meaning of local here?
So local here is just in the sense that if you do a Markov chain on the state space of Bernoulli vectors with exactly n row many ones, and it's exactly two configurations are local if they differ at exactly two locations, right? So you move one bit out here and put it somewhere else.
Okay, the point is as long as the individual moves are bounded in Hamming distance, basically.
In Hamming distance, basically, yeah.
And the Markov chain has to be something that it has to be some kind of Glauber dynamics-y thing, or it just has to be something whose stationary distribution is Gibbs?
Yeah, that'll work. That'll work.
Anything with stationary distribution. Okay, cool.
Yeah.
Maybe one question. Well, so brother, you mentioned, I mean, one benefit, I guess, of the scaling regime that you're considering is that you obtain this Parisi type of formulas, right?
Right.
And I was thinking, it's a general question of how, like, the overlap property, like you're considering, relates in any way to this replica symmetry breaking in the Parisi measure. And I was thinking, like, do you get any information about the maximizers or the minimizers, sorry, of the Parisi, and do they have any funny behavior? Like, is there anything you understand about these things?
So let me try to understand the question. The question is that, okay, this sort of overlap gap that we have, does it actually in turn say something about the minimizers of the Parisi?
Exactly, because we are kind of expecting this, right? In the unplanned case, at least, not in the... like if you get, because usually in the regimes I have considered there are no such Parisi formulas. So I mean that's why.
Right. So I mean yeah. So in general, technically this is sort of one of the big challenges, is because if you study the maximum likelihood, you expect this problem to be sort of fully replica symmetry breaking, and you need the entire Parisi machinery. But whether this in turn yields sort of real insights into the behavior of the Parisi minimizers, I don't quite know. Yeah, I don't immediately see whether it adds something, but yeah, I guess if someone else sees something and they would like to add something, that would be great.
Okay, thank you very much. Yeah.
Subhabrata, there's a question from Jay Mardia. Jay, are you able to say your question aloud?
Yeah, basically I was asking whether, are there other structural properties that are different from like studying the overlap of solutions that people also look at in these contexts and that give anything interesting?
Right. So that I think is sort of very interesting and relevant, right? So I think the reason why overlaps were initially studied is that it became quite clear that this overlap gap property appears in many unplanted problems. So if you look at random optimization problems, then it comes up in many hard optimization problems. And there is a lot of very interesting work by David and his collaborators and many other people, where they have established that in random optimization problems, if you have the overlap gap property between two approximately optimal solutions, then that can be used to rule out a large family of local algorithms. Now, in our context, of course, we are looking at sort of a planted problem. So one can naturally raise this question that, okay, this notion of overlap that you look at, is this naturally the best thing to do? At this point, all I can say is that, well, once we have this does rule out some families of Markov chains. But I think the question maybe that you're raising is that there might be some other structural property that actually points to a barrier to other algorithms. And I think such a thing would definitely be very interesting to look at. But as far as I know, I don't quite know of other generic things that people have looked at.
Thanks.
One follow-up to that is there is the paper by Alex and Gerard and David. I'm not sure the exact author list that relates the overlap gap in random optimization problems to behavior of low-degree polynomials. So you could call behavior of low-degree polynomials some structural
that's
property.
I guess by David, Akash, and Alex.
And Alex, sorry.
Yeah. Yeah, but the crucial difference, I think, is that still in the context of unplanted problems. So I think the issue is.
But you might believe it's believable, right? There would be a nice open problem to see whether overlap gaps in planted problems are related to
low degree
behavior of low degree moments. Yeah.
Yeah. No, that I think is definitely an interesting question to look into.
Or even better if it's related to other algorithms, convex programs or something. Too.
Yeah. Sure. Anything in addition to this.
Like in regression, maybe a comment on this, in regression, we kind of used the techniques for the overlap group to rule out certain convex programs, but we never were able, for example, to do direct thing, which would be much.
Right. So I think the point Elias raises, I mean, sort of, as far as I know, the only cases where the OGP has been examined in the context of planted problems isn't the sort of results that Elias and David had on regression, and then sort of we had in the context of planted submatrices. And then there has been examination here, but so far these results themselves have not been useful to prove barriers directly. The techniques have been useful, but
I thought also for tensor PCA, don't Akash and Reza and Gerard establish them for...
Right. That's very important. Yes, I missed that. So Akash, Reza, and Gerard have the results for tensor PCA as well.
Let's see. Anybody have any further questions for Subhabrata?
Well, since we mentioned tensor PCA, let me follow up and ask if the following is open. Would it be open to establish it for the problem from computer science perspective, which is random SAT or random planted XOR or something like that? Like the sparse analog of tensor PCA?
Yeah, so I don't know actually OGP in the planted context on sparse problems. So I think that's still open as far as I know.
There is something like in condensation phase transition that has been kind of proven that it's kind of similar, I think, in some work from Amin.
I see.
But yeah, I think it's kind of established. I'm not sure what the implications are really. They're more like on the shattering for SAT that we believe it implies a hard region, but I don't think we know a formal implication.
Even for Markov chain type?
That's for the shattering stuff. This is for planted SAT or for random SAT?
So it is. I mean, I think it's definitely for the non-planted case. But
that's what I meant. Yeah. So for the unplanted case, it's definitely there. I guess the question Sam was posing.
I'm trying to remember for the planted. Yeah, I'm trying to.
Yeah, I'm pointing to the refutation of random XOR or recovering planted solutions or whatever.
Yeah, maybe I take it back. Maybe I don't know for the planted.
So at least for the stochastic block model, we know like the free energy landscape pretty well for the planted case. Right. But we had the same problem of what was the starting position of the Markov chain. We wanted to start random and prove that there's slow mixing, but we couldn't do that. I think, Sam, we even talked about this way back.
Yeah, we talked about this way back in Santa Fe, yeah.
Yeah, so that was where we were stuck, that you would like to say, start from a natural position and get slow mixing. we see the energy barriers, but that doesn't actually tell you from a natural starting point.
Is slow mixing really what matters, though? I mean, if it's okay if mixing is slow if you get somewhere close to the planted assignment, right? I mean,
no, but you won't even get the barriers are like separating you from anything overlapping.
okay, yeah, in that case, right.
Yeah, yeah, Chris, we talked about this as well.
Yeah, I guess.
Sorry. Yeah, it's like for how many communities do you have such a free energy barrier? When you say
I guess like 4 or more in the disassociative case.
I see. Okay.
Yeah, we don't know how to do it in assortative.
Subhabrata, there's a question from Matthew Brennan. Matthew, can you ask your question?
Yeah, so this is just a general question going back to tensor PCA. So with tensor PCA, like the OGP, is it right that it's conjectured or maybe proven already to hold above the algorithmic limit of tensor PCA? Like local algorithms are much worse than like the spectral one. Do you know like, so like for this problem for submatrix recovery, it seems like you were saying that you expected the OGP to go up to exactly the algorithmic error, even though it's not proven.
Okay.
Like, do you know what problems in general for which, like, when can you decide whether or not a problem is going to have like OGP matching the algorithmic threshold?
Right. I think that's also very relevant, right? So I think, okay. So I think Matt's question, I'll try to answer it in the context of the specific problem, because I don't recall the exact thresholds in the context of tensor PCA. So what I remarked is that I definitely believe that in this problem, it would be natural to believe that you would have OGP persisting up to lambda going to 1 over rho. But I think the question Matt is raising is it is possible in principle that it just persists beyond that. And that would indicate that spectral algorithms are just better than sort of local algorithms in this particular problem. I think that is possible. I don't quite know whether that is the case in this setting. In the context of tensor PCA, I'm not sure whether the known thresholds are already prove that spectral type things are better. I think the results are by Benarus, Ghesari, and Jagannath, but I don't know the precise thresholds that they have.
Maybe I can say something on this. If like I think it's actually Matt's point is correct. Like we like the work of Focus and Zeran and Reza like kind of proves that there is a free energy well, like not exactly overlap property, but something similar, like a local barrier above the algorithmic threshold, indeed. So like even beyond this. And something we saw with David in the Planet Click is like, indeed, like at least the normal landscape has local barriers above the square root n. So I think at least normal, like, and I can say more, maybe I will wait for a little bit in my talk on this, but I think we kind of expect that like there could be overlap property beyond for some such
some natural problems. Yeah.
And okay, but yeah, I mean, I think it's fair to be fair. Yeah.
Sorry, just one follow-up question. So like, is it possible that this is somewhat related to whether or not the problem's sparse? Like when I hear random 3x OR, for example, I often think that that's the same as tensor PCA, but also like at the same time, it's kind of like a sparse problem like random 3-sat where you'd expect local algorithms to be maybe close to optimal. Is it possible that like random 3x OR might not have this weird property that you can prove OGP above the algorithmic error, even though tensor PCA does? Like, I don't know, this is maybe a very vague question. So
I guess you're wondering if the nature of the problem on the sparse graph versus the dense model can be really different. Yeah, I don't know.
Yeah, for the OGP, even though the algorithmic barriers are like analogous.
My prediction would be that it's not really the sparsity, but it's more the additivity of the noise. Like I feel that like it's for example, the PCA structure that you add noise or the Planet Click that you kind of add noise. Because in regression, we didn't really see this phenomenon, or like, that was more of a linear model. So I'm not sure if it's the sparsity or the way the noise interacts with the signal, but that will be my guess. Yeah.
All right, thanks everybody for those questions. I guess it's probably time to wrap up for Subhabrata's talk. So thanks again, Subhabrata. And